Hello everyone, my name is Yunbo. I'm glad to present our work. The topic is about a window-based streaming graph partitioning approach. Currently, I'm working in the Innovation Lab of Shanghai Pudong Development Bank, and this is a joint work, which is co-work with Southeast University from China and INRIA CCGrid from France and Orange Lab from France. So first of all, this is the outline of this presentation. It is composed by 6 chapters. So for introduction, graph is now related everywhere. The graph structure data is a powerful tool to transform the things from real world to digital world. There are many different use cases, such as traffic network, social network, web graph, linked data, and knowledge graph. Graphs allows for explorations of relationships between entities of interest such as organization, people, and transactions. And graph is the foundation of this. Behind this, distributed graph computing framework supports them applications. The graph algorithm is also able to enhance and improve user collaboration, machine learning models, and explainable AI. So now we talk about what is a streaming graph partitioning algorithm is. So a graph is composed by edges and vertices. And there are two main partitioning methods, edge partitioning and vertex partitioning. Edge partitioning cut the vertex and the vertex partitioning cut the edges. And there's a theory from a paper Power Graph. It said any edge cut problem we can transform to vertex cut and yield better results. So in this paper, we are mainly working on edge partitioning. So the objective is to minimize the replication factor, and at the same time we would like to maintain the load balancing. The replication factor is defined as the total number of replicated vertices and divided by the total number of vertices in the graph. For edge streaming partition algorithms, also there are online and offline partition algorithms. For offline algorithm, it needs to load the full graph to memory, so it couldn't handle the unbounded stream, and after multiple iterations, it yields good performance. However, it's intensive computation, and it's difficult to scalable. For online algorithm, in contrast, it has lower memory footprint, less processing time, lower complexity, and it needs lower computation for partitioning. Lastly, it could be scalable. So this is an example for streaming edge partitioning algorithm. On the left hand, this is a graph, and it transforms to an edge stream, and each time the streaming algorithm consumes one edge from the stream and assigns two partitions. Now we talk about the previous work on edge streaming partitioning algorithms. So OBViews is one of the most efficiency streaming edge partitioning algorithm in previous work. So it can be concluded in 4 rules or 4 cases. We discuss it one by one. So in case 1, UV is the incoming edge. Both of the vertices are already presented in the same partition. So we direct place the edge to partition 1. Only in this case, it doesn't create any replica. In case 2, if only one of the two vertices have been assigned, In order to explore the data locality, we co-located the edges. If there is not only one candidate partitions, we choose a partition with least load from the assigned vertex. In case 3, if neither vertex has been assigned, from a load balance view, we assign the edge to the least loaded partition. The case 4 is the most complex case. If the both vertices have already assigned to different partitions without intersection, then the edge should be assigned to one of the partitions from the vertex with the least load. The HDRF algorithm doesn't change the 3 first cases. In case 4, it employed different strategy. While there is no intersection, HDRF will replicate the vertex with the highest degree. For our experimentation, by using the degree information, HDRF performed well, in particular with the power law distribution graph. It gets lower replication factor compared with oblivious and doesn't increase the algorithm complexity much. Even using the partial degree information instead of full degree information, the performance doesn't have a big change. However, if the graph doesn't follow the power law distribution, the HDRF doesn't show a specific advantage from our test. In some datasets, HDRF is no better than oblivious. So now we talk about our approach, WSGP, a window-based streaming graph partitioning approach. The motivation is simple. We want to do a final decision to reduce the probability of bad decisions. If we want to do this, we need more information. So we use a limited size window to cache a bit more future information in order to exploit the data locality. So the proposed framework is shown here. The case 1, 2, 3 are well done. We don't need to change it. For case 4, we don't direct assign this kind of edges to any partition. We first cache them and do a decision later. So this is an example to show how WSGP works. The incoming edge with vertex U and V, and UV have already assigned to multiple partitions. For oblivious, the edge UV will assign to partition 2 or 4 because the load is the least. And for HDRF, the edge UV will also assign to partition 2 or 4 because degree of vertex V is higher. So HDRF replicates the vertex V to partition 2 or 4. For WSGP, we have a window. We cache them. We cache the incoming edges from case 4. Recall that the case 4 means that both vertices have already assigned, but there is no intersection in one partitions. Them information let us know the potential neighbor of vertex U and V in near future, and we also knew their neighbor vertex has already assigned to current partition or not. This helps us to know how to reduce replica. For example, here, if we place edge to partition 1, the future incoming edge will, with vertex U and X, will direct assign to partition 1 without creating any replica, and so on. There are 2 neighbors for partition 3 and 1 for partition 4. So we will assign the edge UV to partition 3, which yield less replica. For experimentation, we use a full dataset. We developed a partitioning tool inspired by WSGP. There are 2 main differences compared with WSGP. In WS tool, we don't need to load the full graph to memory, so there is no pre-processing time. For example, WSGP load a graph called con or cut dataset. It uses 327 seconds. It's a huge time. And second, we use a bitset implementation, which has lower memory footprint and faster for retrieval. So the graph on right bottom shows for WS2 only for processing fast. WS2 is 2 times faster than WSGP implementation. So in this scenario, we vary on window size. First, we fix the number of partitions is to set to 30, and the foregraph on top shows WSGP by algorithms. By increasing the window size, the replication factor is reduced continuously. And the foregraph on bottom, the throughput for WSGP is worse than the others because WSGP has higher algorithm complexity. In this scenario, we vary the number of partitions. Firstly, the window size is set to 3% of the total number of edges. It's a very small window. So the top graph show with increasing the number of partitions, WSGP can significantly reduce the replication factor, and the foregraph on bottom show WSGP is not so slow compared with other algorithms because in this scenario the window size is very small. For load balancing index, so for all the data sets, all the algorithms yield good load balance. So lastly, we also compared with another window-based edge streaming graph partitioning algorithm, ADWise. We use the same data set as mentioned from their paper, Brain dataset and OCA dataset. Both of them are following power law distributions. Take attention that Brain datasets show extreme power law degree distribution. So the result is shown that replication factor ADWise is better on Brain dataset and the WSGP is better on OCA dataset. For load balancing index, ADWise is their ALBI is inferior than 5%, as mentioned in their paper, and the WSGP is better, so its ALBI is inferior than 1%. We think that if we relax the load balancing constraint, WSGP could further reduce replication factors. So lastly, the partitioning time ADWise is a bit faster than WSGP on both datasets. However, ADWise used 8 nodes with 8 cores each, and WS2 only use 1 thread in a single node. So we use less computing resource and product similar results. So for conclusion, WSGP approach leverage side window, yield smooth replication factor and balanced partitions. And also we found that WSGP is less sensitive to parameter alpha. On the right graph, we can see the overviews algorithm is more sensitive than others algorithms. Why? When we vary the value of alpha. So there is another thing to discuss is about the input order. It is difficult to propose one fit for all streaming partitioning algorithm, such as BFS and DFS order. We think them kinds of order, it's better to propose a specific algorithm to deal with it. For future work, we we will implement parallel versions for WSGP, and release WS2 as open source software. Then we want to integrate it into a distributed graph computing framework with a finer analysis compared with other approach. Thanks for your attention.